Thank you all for being here. I'm Sooyoung at Sooyoung University, and what I'd like to introduce is about research directions that combines engineering with the emerging technologies of AI. So as one of those examples, I would like to define it as engineered artificial intelligence and its potential applications for computational analysis and optimization. So let me just give you a brief introduction of our lab. So it's been about 2 years launching our lab at Sooyoung University, named Industrial AI Lab. And our mission is to develop domain-specialized AI technologies and further realize the AI transformations across engineering systems and industries. All right. First, as you know, the data-driven frameworks are trained on a bunch of data sets, and they might need to see thousands or millions of the observations to make good predictions, right? So this raises a need to develop appropriate methods when specifically dealing with engineering systems with lots of physics and principles from perspectives like generalizability or explainability and feasibility. So by integrating our domain knowledge with AI, we can move forward to the knowledge-driven AI, not just for pattern recognition, but with its improved capabilities for understanding underlying phenomena. So under this motivation, ever since my PhD study, I've defined a new field of study called engineered AI or domain-driven AI, which integrates our domain knowledge into the data-driven frameworks. So more systematically, they can be integrated in 3 different ways. First one is learning bias, which takes advantage of governing relations of the systems into the training neural networks. And we can also leverage architecture bias in designing new deep neural network architectures inspired by engineering principles. And this representation of bias underscores the importance of domain-specific data representation for effective information. So by taking together, we can realize domain specialization of AI for tackling our engineering challenges, which means AI for engineering and at the same time, engineering for AI. So there are many pillars to the engineering workflow, but let me take just a simple example. So let's say I want to run my own bakery, and that makes me consider several things like conceptualization, right? Like how should I make bread and how many? And actually I should do make some recipes and products, right? And I should do some baking and tasting to finalize the process. So in this way, in engineering sense, these several kinds of stages pose research questions like this. And our answers to the questions are associated with neural computation methods, autonomous engineering design, and autonomous manufacturing. So due to the time constraint, today's presentation will cover some of our works underlying the neural computational methods. Okay, so one of the main motivations on neural computation methods is to provide new opportunity in engineering analysis. Because we are often constrained by excessive cost and tedious process, right, in engineering analysis. And it raises some questions that how we obtain real-time and well-performing AI model. And also its continuous nature of gradient-based neural networks can be utilized into an end-to-end manner for entire problem-solving pipeline. So under this umbrella, physics-informed machine learning has been explored in various scientific and engineering applications. So it has been designed to incorporate the governing equations of the systems, overcoming the several limitations of purely data-driven method. So it can be very beneficial in many cases, but challenges remain, such as the lack of capabilities in complex boundary conditions and intercoupled phenomena, and outside the simulation's real-world applicability, and as well as its optimization overhead, right? So I'm going to show you several directions for these. Right, so one representative study falling into the physics-informed machine learning is to learn complex geometry-induced variations. for its expandability for even in 3D space. So we newly designed geometry adaptive internal layer modulation mechanism to effectively capture feature information within the physics-informed learning scheme. So as you can see, our proposed method can achieve the robust and superior predictive performance compared to the other physics-informed learning approaches. So we have more results. In this case, the flow around the object. So as you can see, it can approximate real-time and accurate behaviors according to different location, different structural conditions. And it is also capable of achieving real-time and accurate behavior of airfoils for variations in angle of attack. And expandability for a 3D case in this heat sink example, it can generalize successful approximation for temperature and velocity distributions. So just imagine that if we construct these kind of AI surrogates with like real-time and well-performing performance, it can seamlessly integrate it into various engineering tasks like design, manufacturing, and monitoring, and so on. All right. And another example, in this case, we focused on heat spreading behavior in multi-layered structure. So there are heat flux injection and the convection at the top of the layer with all different kinds of sub-layers with varying materials properties. So that means to figure out this heterogeneous heat spreading resistance, the layer-wise or layer-induced causality should be informed in the deep learning model. So we newly designed the physics-informed AI model that can capture the layer-wise significance by cross-layer embedding and attention mechanism. So you can see we validated our method with concurrent approaches, and our method can show the physically plausible results. But the thing is, as I mentioned earlier, one major challenge of physics-informed AI model is the real-world applicability, right? So one example is the virtual monitoring and mechanical component. So understanding the state of mechanical component or mechanical system is important, right? But it is not fully achievable because of measurement limitations. So for example, a brake system of vehicle is largely influenced by mechanical and thermal stress, right? But depending on different combinations or different kinds of operational conditions. So to reflect the actual operational conditions of the systems, we propose a cascaded physics-informed AI model tailored for a three-dimensional mechanical component. A real-world validation with a commercial vehicle here. And as you can see in this figure, we can virtually monitor this multi-coupled phenomena according to different actual operational conditions of the vehicle. And another example, this is a collaboration with POSCO, and we developed a domain-specialized AI model for continuous casting process. So the continuous casting process is the steel solidification process, and in this case, such real-time characterization of solidifying behavior is ensured for productivity. So we developed our customized AI model for physically valid results while continuously varying process conditions like velocity, the type of materials, and the amount of cooling waters, and so on. And building on this framework, this proposed model can provide valuable information for like process control, which increases manufacturability and sustainability for this continuous casting process. And one more example is real-time personalization of intra-body potential. So in this example, we proposed a specialized AI technology that can achieve mapping the electrical potential field propagated within the human body from just 2D image, which can be a basis for wearable device design, energy monitoring, and even human-mediated wireless communication. So as you can see, depending on different postures and ground conditions, our model can predict the three-dimensional electrical potential distributions in a real-time manner. So far, I've emphasized the importance of domain-specialized AI model, such as physics-informed neural networks, right? But at the same time, I strongly believe that it is important to make the process of developing such domain-specialized AI model more accessibly. So this raises the questions whether they can be somewhat automated. So we defined a novel approach of designing certain domain-specialized AI model, which aims at automated model design optimization. So as you can see, the physics-informed neural networks are generally regularized by the governing equations, right? Partial differential equations. But at the same time, we propose how they are constrained by the combinations of the internal operations within the neural networks. So as you can see in the results, our model or our method enables the learning of governing equations and at the same time, the certain connectivity of operations. So you can see our proposed model keeps evolving to certain combination of neural network architectures. And these are examples of our discovered deep neural networks in physics-informed learning scheme. And as you know, it's not like typical architectures widely utilized in physics-informed neural networks, right? But the important thing is that our discovered neural network achieves the lowest error with the smallest number of parameters. So given that the performance and efficiency generally involve a trade-off, it's quite impressive that our proposed method achieves the both perspective. But however, on the other hand, real-world optimization of the neural networks still matters. And we heavily depend on extensive trial and error exploration by empirical heuristics, right? Because of the convergence difficulties, right? So if you look at someone's workspace here, there are a bunch of trials, right? So this naturally leads to a very interesting question that can summons or can experts' heuristic knowledge can be computationally encoded. So we came up with a very interesting idea that how about developing large language model, structuring someone's results, causes, and actions for language-based reasoning and action framework. So we defined a novel concept of expert-embedded large language model. And we found that our proposed model can generate the language-based reasoning and action in optimizing neural networks with expert mimetic interpretation and decisions. So to evaluate this, we did some optimization game. So for unseen problem, we compared some numerical-based approaches like random search and Bayesian search, as well as a general purpose large language model, GPT-5. And as you can see that they struggled to reach the desired performance, right? And we also validated with actual human, so junior level and senior level students in our lab. And it was quite impressive that the senior level students reached the desired performance less than 10 times. And how about our proposed model? It identified the optimal neural network architectures in 5 times. So our proposed framework, where heuristic intuition, experience, and knowledge meets automated framework, we define it as auto-heuristic optimization. So not limited to the mentioned studies, we are developing a wide range of domain-specialized AI methods for like mechanical understanding and knowledge integration. So they can be applied for like engineering design discovery and smart manufacturing and sensing intelligence for overcoming physical limitations, and also actionable intelligence for embedded system. And the last thing, going forward, there still remain a lot of challenges in real-world applications. So you may refer to our recent review article that conveys several future directions and key challenges, in particular for manufacturing applications. All right, that's all for today's presentation, and I'm happy to take any questions. Thank you very much.